Hey Ramblers, this video covers quite a bit of material, so you'll have to take really careful notes. We're going to go back to section 4.5 and pick up the section that we missed because it deals with a lot of vocabulary that we're going to need as we move into our discussion of planes and lines on the plane, and especially parallel lines on the plane. Then, after covering the vocabulary, we'll move forward to chapter 5 again, where we'll study something called the exterior angle theorem. It's a really important theorem which serves as the basis for the proof of parallel lines and the angles that are associated with them. So please, pause often, take careful notes, and I hope this helps. Okay, in order to understand parallel lines, we first have to start talking about the plane. And a plane is a flat surface. It's a surface such that if any 2 points on the surface were connected by a line, all points of the line would also be on the surface. And that's really kind of conceptual. But you've all seen a plane before. Just imagine a perfectly flat surface that is infinitely wide and infinitely long. Okay, now if you had two different lines on the plane, if they were on the same plane, they would be coplanar. If they were not on the same plane, they would be non-coplanar. So let's think about the second story of Loyola Academy being a plane. Okay, it's not infinitely thin, nor is it infinitely long or wide, but it still gives you an idea of its relationship to the first floor of Loyola. Any line that was on the second floor would not be coplanar to any line on the first floor. So let's take a look at the definitions. A plane is a surface that have 2 points on the surface, blah, blah, blah. Just keep in mind that a plane is infinitely long and wide and thin. It's important to keep in mind what coplanar means. So if they're on the same plane, they're coplanar. If they're not on the same plane, then they are non-coplanar. All right, so imagine we took two lines, line M and line L, and we drew them. Now in this depiction, they're not infinitely long. But imagine they were, that they extended the entire length of the plane. They would divide the plane into 3 regions. One region would be between the two lines, and we will call that region the interior. And any region in here, or any part of the area in here, would be in the interior. Then, if you're not in the interior, then you would be in the exterior. So if you were outside of the two lines, in this infinite region that extends on the outside, then you're in the exterior. Now we point those out because as we start to explain the different angles created by this other line, this transversal, we'll call it line T here, but you'll see that it intersects both line L and it intersects line J. And that is called a transversal. A transversal is any line that intersects two coplanar lines at 2 distinct points. Okay, so let's take a break here. What definitions do you need to know? Well, none of these will really show up in proofs, but I do want you to know what coplanar and non-coplanar are. I also need you to understand what the regions of the plane are, so the interior and the exterior. And finally, you should have a working understanding of what transversal means. So why don't you take a minute, pause, rewind the video to make sure you have those 3 definitions in place. Okay, let's continue then with the angles formed when a transversal crosses 2 coplanar lines. Now we keep mentioning this word coplanar. We will discuss coplanar and non-coplanar more in chapter 6. Everything in this chapter will be coplanar. All right, so when a transversal crosses 2 lines, it creates a total of 8 angles, 4 at this intersection and 4 down here. And because the relationships between those angles are so important, we've given all of them names. The first are the alternate exterior angles. Well, remember the regions of the plane. We had exterior angles were over here and up here. And when we refer to alternate, we're talking about different sides of the transversal. So 1 and 7, for instance, would be alternate exterior angles. Also, angle 2 and angle 8 will be alternate exterior angles. They're in the exterior region and they are on alternate sides of the transversal. Let's look at another angle, which are going to be alternate interior angles. Here again, we're dealing with angles on alternate sides of the transversal, but here they're in the interior region of the plane. 3 and 5 would be alternate interior angles, and 4 and 6 would also be alternate interior angles. At this point, it's not important whether these angles are congruent or not. Anytime any lines intersect a transversal, they create these 8 different angles, and the angles have names, whether or not they're congruent. Okay, so 3 and 5 and 4 and 6 are alternate interior angles. What happens when we get another type of angle called corresponding angles? Now you'll see there are several pairs of corresponding angles, and what's different about them is that one of the angles will be in the exterior and one of the angles will be in the interior. Yet they occupy the same relative position at the intersection of the transversal and the first line versus the intersection of the transversal with the other line. So 1 and 5 are corresponding angles. 2 and 6 are also corresponding. 3 and 7, and finally 4 and 8 are corresponding angles. The last two types are same side angles. You'll have same side exterior angles like 1 and 8, which are both in the exterior and on the same side of the transversal, and 2 and 7, also in the exterior but on the same side of the transversal. Same side interior angles like 3 and 6 and 4 and 5 are both on the same side of the transversal, but they are in the interior region between the parallel lines. Okay, now you really have to make sure you understand all these different types of angles. Alternate exterior angles, alternate interior angles, corresponding angles, same side exterior and same side interior. So make sure you've taken good notes on this. It's going to be really important that you can just identify these in a vocabulary list, but that you can recognize them when you see them in a proof. So we'll have some practice with that in the exercises. Okay, let's move on now to the proof of an important theorem called the exterior angle theorem. All right, as we look at this next theorem, we have to, again, get into some vocabulary here. And that is first to define what an exterior angle is. An exterior angle is an angle created when you extend one side of a triangle. So I have triangle ABC, and let's say I extend side AC all the way out to D. Well, what the exterior angle theorem is going to say is this. The measure of an exterior angle, like right there, is going to be greater than the measure of either remote interior angle. So what that means is that if this is the exterior angle, the remote interior angles will be up here, B would be a remote interior angle, and A will be a remote interior angle. If I had chosen a different vertex to extend, then I'd have different remote interior angles. So you'll notice that no matter what I do to this triangle, this exterior angle will always be greater than angle B or angle A. No matter how I manage to manipulate it, the exterior angle is always the largest. Okay, so the theorem seems to be true, but maybe it's worth going through the proof. Okay, so let's now take a look at a proof of this theorem. The proof is really pretty interesting, and it's unlike anything we've done before. That's why I wanted to show it to you. Not so much that you'll be required to do it, but it's just worth seeing the brilliance of the thought behind it. So they want us to start off by constructing the midpoint of BC and labeling it M. So there I've done that. And then the second step, they want us to construct a point P such that the distance from A to M is the same as the distance from M to P. Alright, since we know that M is a midpoint, I know that these two, BM is congruent to MC. And by the vertical angle theorem, I know that angle BMA is congruent to angle PMC. So, therefore, these two triangles are congruent by side angle side. Since these two triangles are congruent, their corresponding parts are going to be congruent. So let me add some labels just to make my point. Since angle ABM is congruent to angle PCM by side angle side, angle 1 is going to be congruent to angle B by CPCTC. Now let's get back to our exterior angle theorem. If I hide these objects, like this angle marker and this angle marker, let's just delete those. And then these here, I see that angle 1 and angle 2 make up what I had called that exterior angle. So if angle 1, that portion alone, is equal to angle B, the sum of angle 1 and angle 2 must be greater than angle B. Okay, pretty interesting proof. We could have drawn a midpoint through side BA and come up with a very similar proof, which would have shown that the exterior angle has to be greater than angle A. But suffice it to say that the exterior angle theorem is true, and so the measure of any exterior angle of a triangle is greater than the measure of either the remote interiors. So BCD is going to be greater than B or greater than A. Okay, that was a lot of video tonight. So let's take a break. We still have not finished with this section. I mean, it's really dense with a lot of material, but I think it might be a good time to break. So I'll have some exercises ready for you which line up with this work, and I'll show you a couple examples tomorrow in class. Okay, thanks for watching, and I hope this helped.